Good morning, everyone. I'm now developing DSP algorithms for like a year or something, and there's one thing that I kept trying, which is making a delay. And I think a delay has multiple properties that are very important, some more than others. One, for example, is that it must have a feedback loop, so you can always turn that up to make a very trippy sound. And another thing that is important in a delay is what happens if the rate changes, if the user automates the rate of the delay, so to say the distance between the current write index of a buffer, of a circular audio buffer, and its delay sample index in a more technical sense. The important thing about this is when such a rate change appears, the delay must like kind of float over to the new value in the smoothest way possible, and also in all situations. And I feel like that can be very problematically with a circular buffer, because a circular buffer has some properties that feel not very musical. And in this video I want to talk about a solution for that I found. A solution that makes the programming lines when writing a delay effect feel more, closer to the way you perceive a delay in a musical way. So from the perspective of a beat producer or music maker in general or something. But let's just jump into a new build of this project really quickly and just listen to how it sounds. First of all, I want to introduce you with a problem. Let's say we have a buffer of the size 12. So our delay can have the length of 12 samples. Of course, that's not a very logical example, but it's nice to visualize it like that in Desmos because you see the individual steps. So now you have a delay defined of 5 samples. Or anything more like. And of course, your current delay is also on the same spot. But then the user decides to make an automation, maybe to 2. And now we have to go 5 down. So we get a distance of -5. Easy. You would just do some calculations with this number, and that way you could make the current delay walk down to the new value in some kind of way that's hopefully smooth. And it will do that every time the delay changes. Actually, that's just how we perceive it as musicians. But in a programming world, we also have a circular buffer that's very annoying. Because this actually makes it that it will always have to return from the beginning to go on. And the problem about that is that the step from from 11 to 0 is a step of 1, but it jumps to a whole different number. It jumps from 11 to 0. So when you try to do calculations on that, you have a lot of confusing situations that are just not easy to solve. Let's say your current write index is at 11 and your delay is set to be 2. That means 11 minus 2, which is 9. So you have a delay at the current buffer's index of 9. And maybe your current delay is also there. What happens if the current delay is before? Then we see that there's a distance between the current delay and the delay that is our destination of 2. Easy, we can use this number to make a calculation and it moves over. It would also still work if it comes from the other direction, because then it just has a negative distance, and we can use the same algorithm or a very similar one to just get there. But what other situations are there? Let's say the right index is in between of them. What would happen if we really used this number now to get there? It would go forwards and it would cross the right index, and that would mean that it jumps very hard from present to the fastest pass of the whole buffer, which can be very pasty, and from there it would go on to the destination. And we don't want that. Obviously you see the solution immediately. You would have to go backwards, like here, then come out here and then go here. And I know it's not difficult to come up with a formula for that. That's really easy. But the thing is that this is just not really intuitive. And if you think of a delay, you don't think of it as some kind of thing that starts from the beginning all the time. You think of it as a continuous motion in the same direction, which is being a delay. If you know what I mean from a musician sense. So how do we get the circular buffer to appear more musical? Our goal is to make a visualization, or more like a representation of a circular buffer that works more like this. If the next frame or the next sample comes, then the value that has been in the present point will appear like it shifted to the next index value, or to the second, or third. And more values come from here, because this is always where the new samples spawn, where this is the most present point of the delay. And as you can probably imagine, this is the most past point of the delay. And you already see what's the advantage of that, because now you can just say, if you are searching for the current delay position, you could just say, let's say it's 4, 1, 2, 3, 4, and it would be this sample. Let's say you have another sample and it's here, I mean another index. So this is where the delay is currently at, and this is where it wants to go. Then it would just go over here, and it would never have to cross the present point, because the present point will never be in the way. And I wrote this little program to visualize that. By the way, if you're asking yourself why it always has multiple colors, that's because this also represents the linear interpolation of the index values. For example, if we take a value that is very close to the floor, we get more of the strong color on this side, or we go the completely other way around and we will get more of the color on the other side. And that happens for the index for finishing it. Oh, I was a little bit too slow there. As well as the index of the current delay, which is represented in yellow here, and this is the destination, and the destination is also represented as a floating point index, but the index that writes to the buffer, of course, can just stay an int, because it's always on the same spot. In the header file of this very simple GUI animation JUCE project, I instantiated a sine delay object that I call delay. For each frame, a new random sample is being generated that can be between -1 and 1, so it's kind of like an audio sample. And this sample is being written to the delay object. Then we call the repaint function, which just paints the thing that you have just seen. And then we increment everything in the delay that has to be incremented. The header file that I will explain in the following has a namespace called HDL, and it has 3 different sections. First of all, it has the basic functionality, which is part of a buffer class and a delay class. Then it has a lot of different delay implementations. These override a specific method and have their own behavior for rate changes. And then we have a class for visualizing the delay, just so we can see it on the screen when I compile. The most important thing here is the buffer class. When you make a new buffer, you can give it a size, or you can just give it no size and it will automatically give itself this size. It has an index which starts at 0, and this is the index that will write to the buffer for each sample. It has a size, and the buffer is being resized to the size. This is a vector of type objects. So you call the write method when you want to write new samples to the buffer, and it will just get to the current index of the buffer and write the sample to it. It has a read method that has an integer which is meant to be an index value as an argument. And now it gets interesting, because this is actually what makes the difference between my buffer and a normal buffer. This is not being put directly into the buffer. First we have some calculations on that. We take it and we get index minus e, and you already see where this is going, because index minus e implies that this is supposed to be the delay from index. And now we can potentially get negative values, because if you imagine the index could be something like 0 and this could be something like 5, then it would be minus 5, makes no sense. Then we would say if e is smaller than 0, then it will be pushed up. So this is basically going the other way around. While the circular buffer always goes up and then flips down, this goes down and then flips up. And by doing the opposite motion in this way, we can make it more intuitive. Here's the same method, but the only difference is that we take a float point value instead of an int, because I only use the int for tests. And then we apply a normal linear interpolation to get the right sample. I overloaded the operator with the ++ symbols with so that it always increments the current index and lets it flip back to 0 if it reaches the size. So this is just basic functionality of a circular buffer. The delay object gets a size as an argument and put that into an integer size. It also has 2 index values, the current delay index and the destination of the delay's index, which both start at the same point, and these two also start at the same point as the start point of the buffer itself, so everything is lined up at the beginning. Also we have a buffer object. This is an object of this class in this class. This method is being used to just write to the buffer the current sample. It's just being passed to this object. There is a set destination method where you can set the delay in samples. There is get destination to get this value back and get delay. Notice that there is no set current index or something like that. We can only set our destination. The ++ operator method works a little bit differently than in the normal buffer. It has a follow method, which is a virtual function that has to be overridden, as you can see. So we need to make classes that inherit from delay in order to describe how the current index should follow the destination index, and then we increment the buffer. By the way, we'll come to the project in which I transformed this to something that makes actual sound very soon, And I want to say about that I also changed some aspects about these classes, and you will see that very soon too. And that's why I will also skip these for now, because I improved them when I could actually hear the outcome of the delay, and I will only show you the ones how they ended up. But I can show you the visualizations really quickly. This class just has one method, a static paint method, that is used to paint the delay on the screen to make tests like this. It gets a reference to a delay object, a reference to a graphics object, and a reference to the current bounce of the screen, or more like the current bounce of where it should be drawn on this not on the screen, I mean on the window. Yes. So first of all, we get some basic variables from our bounce and from our delay, for example its size. And we decide for an increment value for each index, because we'll go through all indexes very soon. We prepare the size of the text output, and we get some useful delay data from the delay object. For example, its destination index and its delay, and then we perform linear interpolation on that. So we can draw these parts of information differently later in our loop, where we will loop through all index values. Then we define some colors. I know. If this was not a static function, I could move this out of the method, and then it wouldn't have to be loaded every time the method appears to be activated. But I must admit, this is just a small visualization and I'm a little bit lazy on this part. The actual sounds is more important to me, so it's okay if this is not very optimized. Now the buffer loop. First of all, we define an area, and this area is for our blocks of audio, and then we reduce this area a bit so it has some spaces around them, which just looks nicer. And then we set the corresponding colors if the index has some specific value. We draw it and we go on with the X for the bounce. So we won't draw a rectangle on another rectangle or something. And then we also print some text values and a little function that makes the text value more readable, because if you don't do it like this, then the floating point numbers can have a lot of decimals, and that would look very bad. But of course, you want to do how I actually made it sound so cool, and which changes did I apply to it after I transported it from the purely visual domain to the actual audio domain. This time, let's just start at the process block function, where everything is supposed to come together in an audio application, or more like in an audio plugin. The first line is just that we set the destination relative of the delay, and you see this is already a method that I added after I ported it, because this method was not in the delay object when we saw it the last time. And what does it do? It's actually pretty easy. So you give it some normalized parameter, so one that goes between 0 and 1, and it's calculated, it's multiplied with the value max. And max is always defined as size minus 1, so the maximum index value possible. So if this was 1, then this would be the maximum index. And if this is 0, then this is 0. So this can set the destination in a relative way. You can also set the destination in samples still, of course. And when I port this delay to work with tempo sync, then I will probably use this method rather than this one. But this one is easier for just testing very quickly if the delay works. Then we have the double loop, the double for loop, which goes through all samples and all channels of our audio buffer. And for each of them, it gets a write pointer to the current sample of this channel. Then we write the sample to the delay, and then we apply an addition to the current sample with some sample from the delay buffer, which is the sample that the method readDelayValue spits out. It also takes a channel, which is also something new, by the way. I added the possibility that the possibility for a stereo setup to the delay object. It's not part of the buffer object, by the way. And the readDelayValue method that only takes a channel gets to you the current index, so it basically just performs the read method on the current index and the index. And here you also see something that I changed. In my last implementation of the buffer, the index was part of the buffer, but now I put it into the delay object instead, because that means in a stereo setup that I don't have to increment the index twice for each buffer, even though it will be on the same value anyway. So now when we go to read, it's almost like before, and the only difference now is that this index is not a member variable anymore. Once we have added the delayed sample to the current sample, we can increment all values from the delay. I think I've said everything important about the changes that I added to the buffer and delay class, but if I forgot anything, I will just go through these very quickly. Of course, also a setChannelCount method, where you can set the channel count and then it will resize the buffer. Maybe important to note, the buffer is not just a buffer object now, it is actually a vector of buffers that can change its size, of course, because if the plugin instance is being dragged to another track that has a different channel count, then of course we have to update this. Now I want to talk about the different implementations of a delay that I made, so I can just show you how different the rate changes can be interpreted. But first of all, I have to tell you some other thing, which is I took away the arguments from the constructors of the buffer and the delay, because when you make a new class that inherits from delay, then you can just set your own arguments, and these arguments are only for like helper arguments for the algorithm that changes the rate. Now let's look at the simple delay example. If the delay index minus the current index is smaller than steps, and steps is an argument that we get here, then we just override the current index with the delay index. So this line basically means this is a really small distance, so why not just make it the same distance, or like 0. Else C index is smaller than D index. That means that the current index is on a smaller number than our destination. Well, then let's just make it go up by the steps that we defined. And what if it's bigger? We just go down these steps. So what makes this delay implementation so simple is that it just doesn't have a speed. It just says either go up or down, or basically stay at your position. I prepared these objects in my plugin processor header, so we can try the different delays by just uncommenting them. probably as expected, it's very simple. When you change the rate, it will just go to the new rate at a constant speed. And that sounds a little bit weird compared to the good delays that you are used to as a musician, which change in a more fluid way, so to say. But there was another problem. When we went to one direction, it sounded very differently as when we went into the different direction. That's probably because the circular buffer currently moves into one direction, even though we don't see it here, it does that still. So if we move towards some direction with our current index to the destination, depending on if this is a negative value or not, I mean the destination minus current index, the distance, then it will sound very different. So what could we do about that? We could take the same concept, but instead of just having one steps value, we separate it to steps up and steps down. And we also find the minimum step. We use the minimum step thing for the if statement when to do this. But now, depending on if current index is smaller than its destination or bigger, we either use steps up or steps down to get a different sound for both of them and have them both controlled. As I already mentioned a little bit earlier, it's a little bit of a problem that the speed is so constant. So one idea about how to go about that would be this method. First of all, we get an argument speed, and we also want to know the inverted function by the maximum index. Better to visualize this in Desmos really quickly. Suppose you have a buffer of some size, like 12, and you have a current index C and a destination index D. Now, as I told earlier, the distance is described by D minus C. And to get this in a relative scale to the whole size, we say the distance divided by the maximum index. So now if the distance is as big as the whole buffer, we get 1. Whereas the more we reach our destination, we get 0. This is exactly what I did here. And then I multiplied it with the speed factor. Let's hear how it sounds. As you might have noticed, the problem about this is if the distance is really big, then of course the number 1 times the speed factor will be the maximum speed. So let's say we change the rate from something very small like 1/32 notes to a whole bar, then it would jump really hard there, and it would slow down of course till the end. But this beginning is just a little bit very high pitched. So what if we, let's just skip that for now. This is just the same as for the last method. Speed down, speed up. So the speed is different depending where we go. You've seen that already. But let's get back to the problem that I want to talk about. Speed mix delay. Now it has two arguments. It does not just have a speed, it also has a mix value. And it has a current speed and a last speed. First of all, we get the relative distance. Now it gets interesting. The current speed, both of these start at 0, is the last speed, so 0 plus the mix parameter times rel distance times speed minus last speed. You probably know this. This is the typical mix algorithm that is being used for dry, wet knobs and stuff. And you can also use it in this context because it will make the current speed be considerably slower than in the last implementation when the distance is really high. Then we increment the current index by the current speed, and we put the current speed into the last speed, so when this method is being applied the next time, we will have a new value in here. Holy shit, there must have been something I didn't prepare for. Well, I will look at this a little bit later. It more or less works though. Another idea to improve the performance for long delays would be changing the way the distance is being interpreted. For example, give them some kind of triangular motion. And it could look like this, where you would say, if the value is very big, then take this. As you can see, the nearer I go, it goes to 1, and in the middle of the buffer, it is at more or less 1. And then notice the other value that goes down from 1, from this point, back to 0. So we basically make a triangular motion. Something that went like a saw wave before now walks like a triangle, and we will hear how this sounds after we have looked at the method really quickly. This is just this line that I was just talking about. And then we also wrap a 10H function over it, just so it's a little bit rounder, and we apply our speed like before. Well, I don't want to show you all of these implementations because I think they would take too long, and some of these aren't really that spectacular, but I maybe should go about the last two ones. The sine delay one is the one that I like most at the moment. The idea of the sine delay is, instead of using just the distance, we use a sine function to calculate the way it should move, and that way get a smoother way of interpolating these rate changes. It basically just looks like this. And it sounds like this. One thing that I like about programming is that you can interpret a lot of these things in very different ways, and that it's very creative. It's just like making music itself. If you are familiar with synthesis, then you probably know this function, which transforms a bunch of sine waves to a saw wave. And this is used in the analog world more than in the digital one, but the saw waves that derive from this are always very pleasant to hear compared to a normal saw wave, in my opinion. And it's actually without all this stuff and a different way of skewing it between -1 and 1, but we won't go over this now. I just wanted to show you this wave so that you understand the last delay algorithm that I came up with, because this wave has the property that it does not go into one direction all the time, but it always wobbles between different values. And I wanted to hear how that sounds. So I prepared a lookup table with the information of this saw wave. And when a new object of wobble delay gets initialized, then this object gets 265 samples, and the samples are being calculated and written into the vector. And then I also perform some stuff to normalize the wave, because I know someone told me the formula for getting a normalized wave of this in general, but I forgot it, and now I have to normalize it in this noobish way instead. And then we just get the relative distance, like in most of the other algorithms, calculated together with the speed and the maximum index from the vector to a new index value, and then we use the index value on our vector to get to the corresponding point in the lookup table. Let's see how this sounds. So now you really heard how this algorithm has more of a wobbly tone. When you change the rate, you really hear how it kind of goes through different waves of speed instead of just moving towards its destination. Normally it does some weird stuff. However, I want to make a little conclusion about all this. I've been sitting on this for like a week or a little bit more, very intensively, and I've been trying to work with delays before, but have failed to come up with this. And I think that it's pretty awesome. I know there is a downside to this. The downside is that by transforming all these operations on the buffer for each sample just to make it more comfortable, it might be a little bit unoptimized, and in many cases do a lot of calculations that are kind of not necessary. But I hope you also saw that it made the actual implementing the implementations of the delays, first of all, super readable and understandable, and secondly, very fun to implement actually, because you can make a lot of stuff with just a few lines of code. So in order to test your delay rates, I would suggest using this method, or more like my class. And then when you found something that you like a lot, you can still go ahead and kind of try to optimize it and make it behave more like a normal circular buffer again. So you can just have a really fast and cool performance plugin and everything. But let's see how this plugin currently performs in the audio performance meter of Cubase. And you see, whatever it is doing, it's definitely not doing a lot. It's really okay. Even though this is not a small buffer, it has a size of 44,100 samples on a sample rate of 48 kilohertz, so it's almost a second. I also want to take this opportunity to discuss a little problem that occurs every once in a while, especially in the Discord forum, in the Discord chat of the audio programmer, where we always talk about stuff that is going on currently. I've been criticized sometime for not utilizing the JUCE framework hard enough. In terms of, for example, when I want to have an oscillator, then I'm criticized because I'm writing my own oscillators, and I could imagine that some people might criticize me for making my own buffers and coming up with delay algorithms myself, because JUCE has some delay algorithms that already work. Someone already made all the work, had all the thoughts I already had, and solved all the problems. For example, the problem that occurred earlier in this video, where a vector went out of bounds and threw an assert. Yeah, that's true. JUCE probably has more stable methods and classes for mostly everything, and that's pretty cool. But I hope you've seen one thing, and that thing is really important to me. We have had all these different implementations, and all there were for were just the difference in behavior when the rate of a delay changes. That's a detail about a delay. That's not the main part of the effect, but it's a property of a delay that is very important to the quality or how it is perceived. And as you have probably felt, it makes a lot of difference, for especially the hard difference between the simple delay and any of the delays that had a curve in them. And I'm not sure if I would get to the same level of detail if I would just use the JUCE methods all the time. They would probably make one solid solution to this, but not give you all these options that I just had. You know, like I could approach this problem from really different angles by having my own code base for all that. I could use lookup tables, use sign functions, use the difference, or just use if statements to see if I'm bigger or below the destination, and a lot of other stuff that could probably be used in this case. So that's pretty powerful in my opinion, and I like this approach a lot. And I know sometimes it's really worth it to use the JUCE functions, especially if there is no creativity involved. But whenever I feel like some part of the DSP or the GUI algorithm has some kind of room for imagination and creativity, then it's definitely much cooler to just write it yourself. And maybe I will someday be some part of a team, and they will say to me, yo, what if you just make a nice algorithm, but only for the rate changes of our new delay? And I'm like, yeah, I did that very extensively. You can be sure that I will come up with something. So I think that really can go a long way for my personal future. Maybe I will not get stuff done so fast now, not have 100 finished plugins constantly or immediately, more like, but therefore I will gain some background knowledge about how stuff works, and I think that's also really important as an audio programmer. And I say that as a noob, I know, but that's just my opinion at the moment. Yeah.